The 24th video in the video series of Orbital Mechanics with Python. This one I'm going to be going over escape trajectories. So I'm going to first start with impulsive escape maneuvers, where the definition of impulsive is when you have an instantaneous change in your velocity vector. So from one step to another, your velocity vector changes, but your position vector doesn't. And this is a good enough model for most cases. Obviously, you want higher fidelity. You want to go ahead and model, say, if you're thrusting for a certain number of minutes, you want to go ahead and model that. But for the most part, for most applications, you can assume instantaneous, and that's fine. So the first thing I want to show is a difference whether you're in some orbit and you want to escape when you're at perigee or apogee, and show how the delta V is actually going to be different when you're in an elliptic orbit, if you want to do that. So basically the goal of what I want to get to in the script is to show you how to model an impulsive trajectory to escape, so at escape velocity, and then to show you over here kind of the output, how you can see that there's a bigger delta V when you do at apogee versus perigee. So first things first is to create an orbit. Actually, I want to show what these orbits look like. I chose a really eccentric orbit just for the sake of showing a big difference between apogee and perigee. This is what it's going to look like. So this teal one is your original elliptical orbit, and this green trajectory is if you want to escape at perigee, and then this black one is if you want to escape at apogee. So that's what that looks like. So first you have to make your initial conditions, where your semi-major axis is going to be the radius plus 26,000 kilometers. This is an arbitrary orbit. I just wanted to make one really eccentric. So 0.74 eccentricity, and the rest of these are arbitrary as well. But actually not arbitrary. So when you're at apogee, you're at 180 degrees of true anomaly, and then when you're at perigee, you're at 0. That's just the way that true anomaly is defined. And then I'll talk about this one after I get through this first, but this rotated one, basically, I just wanted to show that sometimes you want to escape at perigee, but you actually want to make sure that your escape trajectory is actually angled in the right direction to where you actually want to go. So I'll show that a little bit later in the video. But first, you just want to calculate your circular velocity at your position. So as I showed in the last video, the way to calculate a circular velocity is just square root of mu over r, super simple equation. So you have your Earth mu value, and then you divide it by the norm value. So this is a norm, this isn't a vector, this is just the magnitude of the vector. So the magnitude of your position, and to the power 0.5 will give you a square root. So doing that for both apogee and perigee. And then you want to calculate the normed velocity vectors, where the normed vector is the vector that points in the same direction as the original vector but has a magnitude of 1. And how you get that is just you take your original vector and you divide it by the magnitude of the vector. So I'll show you, it's a super simple, but I'll just show it. The normed function that I have. Where is it normed? Yeah, where you just have your array and you divide it by the norm of the array. So mp.linout.norm. And I believe this library uses the 2 norm unless you specify. There's a bunch of different types of norms, which maybe I'll post a video about because that's an interesting linear algebra concept. But for now, it's just a 2 norm where you square root the sum of the squares. That's what the 2 norm is. So you have your normed velocity vectors, that's what that is. And then you want to calculate your escape velocity at your certain position. So as I also went over in the last video, the escape velocity is just the square root of 2 mu over r, which I just put in a function again, escape velocity in the tools file, where you go ahead and pass in the norm, again the norm, not the vector, but you just want the norm of the vector. So escape velocity, where did I put it? Yeah, super easy math, square root 2 mu over r. I just made it a function. And so you want to calculate your current velocities as well. So again, you're taking the norm of your current velocity vector. Pretty straightforward there. And then you want to calculate the escape trajectory vector. So after you thrust, you're going to multiply whatever your norm vector was, so the vector that's going in the same direction, but then you have the magnitude of escape velocity, which as I said in the last video is defined as a velocity necessary to achieve parabolic orbit. That's just what I define this as. You could make this to have more, to be a hyperbolic, but just for this example, I made a parabolic. And then you just print out all the values, and then that's how you get these. So you can see that your current velocity at apogee, I'm going to put the plot side by side. So when you're out here in this orbit, your current velocity at apogee is going to be 1.3 kilometers per second. So not very fast, especially compared to when you're down here. Where the circular velocity, if this orbit was actually like this, circular like that, your velocity would be 2.64 because it's a more energetic orbit since it have a larger semi-major axis. So the orbit would be, say, this big instead of that big. And then the escape velocity, that amount of distance away from the Earth, is at 3.7 kilometers per second. So taking the difference, you would need to change your velocity by 2.38 kilometers per second in order to escape. Whereas when you're at this perigee point, you're actually going at 9 kilometers per second, so a lot faster. And so your circular velocity, if you were in a circular orbit here, right close to the Earth, would be about 6.8 kilometers per second. And this one is smaller because, again, this teal orbit is a more energetic orbit than one that would just be right here hugging the surface. And then the escape velocity there, it's a lot closer, so escape velocity is a lot higher, 9.6 kilometers per second. But because you're going so fast, you have such an energetic orbit, that actually is only a difference of 0.65 kilometers per second, so it would take a lot less time in order to do that. So yeah. Want to show that first of all, and then I also want to show a line in the escape direction. Like I said, sometimes you have to accommodate for your launch vehicle, so your launch vehicle will put you at some orbit around Earth, but maybe you want to rotate your orbit such a way like this, where you align your perigee in order to escape in the direction that you actually want to. So say you don't want to escape in the direction of where the green trajectory is going, you say you want to go more this way, you just have to make sure you account for that. That's just something I wanted to show, and that's just all I did here, where all the parameters of this orbit were the same, except for the fact that I just gave it a 45 rotation in the argument of perigee. I can't remember if that argument of perigee or ran, but one of them just rotated it, just to show that you need to be able to account for that when you're actually choosing an escape trajectory. And you have to account for the moon because as you're escaping, obviously the moon is going to be you're going to cross the moon's orbit. You might not cross where the moon is close to you, but you're going to cross the orbit, so you have to make sure you know where the moon is. And sometimes you actually want to use the moon for a flyby to just change your velocity vector, gain some velocity. But I just want to show that you have to account for it, basically. Because if you don't know where it is, I want to show this. If you don't know where it is and you didn't expect it to be there, it actually perturb you a lot. So like this green trajectory, as it's going out, it's actually passed quite close to the moon, and you can even see how that bent that trajectory quite a bit. And I also wanted to show the codes for that. Let's see once this loads, because it actually affects it a lot too. So first of all, these codes are for this green escape trajectory. So it starts at 1 because that's how I define initial conditions. You start a parabolic as a parabolic orbit. So the eccentricity. So basically, the eccentricity is that, so as it's going out towards the moon is given an extra tug towards it, so it's getting more eccentric. It's gaining velocity out there, and then once it reaches past the moon is then pulling it back towards the Earth, so the eccentricity is going to decrease, and you're not a parabolic orbit anymore. Like, this is a very small difference, and other perturbations will probably get you to not come back to Earth. But that's something you have to take into account, is where the moon is, because this could, if say this the spacecraft flew a lot closer to the moon, these changes in the parameters could be a lot greater. And again, here, change of inclination by 2 degrees, that's actually pretty significant if you don't account for that. Oh, I just show the Python for that real quick. So I just made a new perturbations dictionary where it's just the moon gravity, where here this included, actually no, this is different. I was thinking about the next problem. But this one, just add the moon as one of your perturbations. Get your original states. So this is just concatenating. So all this does, since these are Python lists, just go Rx, Ry, Rz, Vx, Vy, Vz, just making them lists and concatenating them to get the original state. So that's for all 3 of those orbits. And then obviously just orbit propagator instances, where the rotated one I just pass in as codes instead of the state vectors. And then calculate the codes, plot the codes, all that good stuff. I've explained what this command means in a previous video. Just basically just getting the trajectory data of the moon from one of the orbit propagator instances, because you calculate where the moon is with the SPICE files. And then just plot in orbits like usual. And that's how I made these plots. So this plot, obviously, this is the same plot, just I just showed different angles of it. And then the codes. So then that's pretty much it for the impulsive escape maneuvers. And now I'm going to go to low thrust. So the low thrust is an outward spiraling trajectory. I showed a little bit in the last video. But you have a lot longer thrust time, where for impulsive, those thrusts tend to be in the order of minutes. These are the order of, say, hours or days. So a lot longer, and you have thrust in the order of millinewtons, because it's an electric propulsion system, so they have a lot less thrust, but they're a lot more efficient. So I just want to show real quick what that looks like, this spiral, where each time you spiral out, as you're getting farther away from the Earth, you're farther away from your previous spiral, because the gravity of the Earth is getting weaker, and your thrust stays the same, assuming your thrust stays the same, obviously. So that's going to make a difference like that, and I'll show the codes in a second, where it's more clear to see that in the eccentricity. So this thrusting model, I went over this in a low thrust video, but it assumes that you have just a constant thrust in your velocity direction, and this is not an optimized way of doing this, but this will still get you a good ballpark delta V to be able to do some preliminary analysis. So when you optimize it, you're going to have less delta V, or whatever you optimize for. Maybe you optimize for less thrust time or just less travel time in general. So let's see, what do I have next? Oh, I want to go over the Python real quick. So this is a trajectory. I'll show you how to get that trajectory. Typical imports, obviously. We need a start date on this one because, need a start date on the previous one because you want to know where the moon is. So you have your perturbations dictionary. It just looks just like the low thrust video I made. You have your thrust, your ISP, thrust direction, and then this one I'm just adding the gravity of the moon. And I'll go over this, but you have to add, or if you want to, or you can just keep thrusting until some sort of time. But I have escape velocity defined as a stop condition, so whenever escape velocity is reached, get out of propagation. This is just an arbitrary value for mass. Initial state, once again, arbitrary. This is just 800 kilometer altitude, basically circular orbit, 0.01, with a little bit of inclination. And then just create the instance of orbit propagator, and then it'll stop propagating when you reach the parabolic velocity or when eccentricity equals 1. I want to show, I think this is a good time to show the escape velocity stop condition. This is really close to very similar to what I did in the stop condition video. But basically just you want to add another one that says check escape velocity. So I just put this all in one line, but basically, so if the escape velocity is less than your current velocity norm. So what this is, it's taking the norm value. So you're into the escape velocity equation, you just want to put in the norm value of your position vector. So here's your position vector at this certain step. So self.y is your state, so you want to grab your current step and then 0, 1, 2, which is your position vector. Take the norm of it, pass it into escape velocity equation, and make sure that the mu, because this isn't necessarily at Earth, to make sure you have your internal mu from your internal central body. So you want to check if that is less than this self.y. Once again, this is your current position, or this is your current velocity because this is 345. That's your current velocity. So if this value is the norm of your velocity vector is greater than escape velocity, you've reached escape velocity, and then print the stop condition to the terminal and then return false. You can, if you need a refresher on this, go back to the stop condition video that I made, and this I think will make more sense. And then from that, or since that video, I've added this stop condition because I found it annoying that I have to have this print statement in every single stop condition, so I just made a new one where you just pass in a parameter, and it tells you how long it took for the stop condition to be reached. So going back to here. So plot the altitudes, I went over that in another video. Plot the 3 trajectory, which is what you saw with the spiral. Calculate and plot the codes, all pretty simple once it's already implemented in orbit propagator. And then calc apoapse and periapse, and then plot. So I'll go over those plots real quick because they're pretty interesting. So that's a spiral. So this is the codes for when you're thrusting. So as I said, your eccentricity actually is going to increase in an exponential fashion here the farther away you get from the center of the Earth. So zoom in here. This might zoom in a bit too far, but we'll see. Yeah, you can see it stays pretty low for a while, and then it just starts with that exponential growth. Just wanted to show that. And also the inclination, this is just due to the moon, and these are very small values, so it doesn't really matter very much. And then this also, so the way that the orbital parameters are defined is a bit different with hyperbolic and parabolic orbits. Just the geometry of them is a lot different. So kind of like this true anomaly, this wouldn't make sense kind of when you think about it intuitively with elliptic orbits. But I'm going to make another video when I go a lot farther in depth in the geometry of hyperbolic orbits, because as I said, it's quite different. And these other parameters just has to do with the definition of them, so it makes them look kind of wonky, but the eccentricity is mostly what I wanted to show. And then this one is just this escape, where I'll show in the script, but basically I just wanted to show you a case where, say you stopped thrusting a little bit too early, maybe your engine died, or you just thought you had enough velocity just from your orbit determination, but you actually didn't. You can see how you're still confined to the gravity of the Earth if you stop thrusting too early. And this is the orbit of the moon, and then, yeah, so you can see the spiral. So this is just a very zoomed out version. I just wanted to show that, if you stop thrusting too soon, you're still confined. And then the apoapse and periapse. So you can see that these are kind of bouncing off of each other. So whenever they're equal, that means that you're at a eccentricity equals 0, which is circular, so it stays pretty close to circular the whole time. But then you can also see the kind of exponential growth as you get going out farther. And like that, you can very much see. And also, again, has to do with the definition of apoapse and periapse when you get to parabolic and hyperbolic orbits. Oh, just one quick thing. I just wanted to show kind of the coast phase here. So I created, so this is all for the low thrust stuff. So I just want to show the coast phase that I had. Just the only perturbation is gravity of the moon, where you have, so this coast phase 1 is when you just take the final conditions of the low thrust trajectory and you plug them in as the initial conditions, just with the moon perturbation, and then with no thrust. So I had to make a new, you have to make sure you make a new perturbations dictionary, because if you didn't and you just use the other one, you'd still be thrusting. So you don't want that for this one. And then the second one is, say you stop thrusting 100 steps before that, where I made the dt equal to, let's see, 100 seconds. So if you stop thrusting 100 times 100, spacing out, you get the point. Before that, then you're not going to escape and you're going to come right back, especially because the moon's tugging on you, so it acts as like a little extra force of gravity on top of the Earth to kind of pull you back. And again, other perturbations could take into effect, like end bodies of the planets, but just wanted to show that if you're only modeling the gravity of the Earth. And then again, just extracting the moon's trajectory from all this, and then plot n orbits, just like usual. So yep, and then I wanted to show there's also some multiple impulsive orbit raising maneuvers that people have used. So this background picture, this isn't what it is, but you can kind of see it. So say you started in this smaller orbit and you just wanted to raise your orbit a little bit, not to escape, but then you just raise it a little bit more like that. And then I'm going to show that this space IL is actually how it got to the moon. These are the maneuvers that it did. So this is just on the NASA website. I'll go ahead and post a link to it. But this is what the trajectory looked like of that spacecraft. So it started in this 400 kilometer orbit, just thrust a little bit, get farther out, thrust a little bit farther out, until eventually, and obviously they had to time these very well, so then when they would make this final thrust, it goes all the way out, the moon would be there in order to get captured by it. So I just want to show like kind of, this is an example of a little bit in between where they do multiple thrusts but it's still instantaneous. Just wanted to show that example. That's also something that people like to do. So there was a lot in there, but that's it for this video. In the next video, I'm going to get into, and this will take a couple videos, into Lambert's Problems. So something that's very important in orbital mechanics. It has a few applications, but basically this problem was originally proposed by Johann Heinrich Lambert in the 1700s, where if you have two position vectors, so say you have a spacecraft that's in one position at one time, and then some finite amount of time later, it's in another position, so you have two position vectors and one delta t in order, so from that you can also go ahead and estimate what the orbit of that spacecraft is. And this is mathematically proven that you could take those pieces of information and go ahead and find a solution by Joseph Louis Lagrange, which Lagrange, if you heard Lagrange points, same guy, so he's an important person. So yeah, and it's going to take quite a few videos, and there's actually a number of solutions to Lambert's problems that will give kind of differing answers depending on what assumptions you make. So it's a pretty interesting problem. And the applications are, say, transferring orbits. So if you want to go from the Earth to Mars, the Earth is, you have the position vector of the Earth when you leave Earth, and you have the position vector of Mars when you want to get there with a certain time of flight. So then you can calculate what your trajectory would look like by getting the velocity vector necessary to get there at that time. So yep, that's it for this video, and thank you for watching.